hypothesis is true. So assuming that the null hypothesis is true, what is the probability that we will get that value? Now remember, when we did null hypothesis is always where things are equal to. So we are making the assumption that we know the population mean, or the population proportion, or the population standard deviation, whatever I'm doing my hypothesis test on. We assume we know it to be this value, so it equals something. Then what's the probability that we're going to get something that extreme happening? It makes a difference as you calculate out your probability value, your p-value. It makes a difference if I'm doing a left-tailed, a right-tailed, or a two-tailed test. So it's extremely important to pay attention to what type of test you're doing before you start calculating out that p-value. So if we look at how to find the p-value. Oh, before we find it, I guess we need to know what we're going to do with it. Once we're trying to figure out what we know from that p-value, the null hypothesis is rejected if the p-value is very small. And again, that alpha value will be given to you in most of our problems, but typically if it's not given to you, you're going to use your 0.05. So if your p-value, your probability is 0.05 or less, or whatever alpha is or less, then if that's the case, we are going to reject that null hypothesis. On the other hand, if it's larger than that, then the null hypothesis is going to have a fail to reject. A little mnemonic, and I've noticed, or a little memory tool, I guess it's not a mnemonic, but a little tool that people have used. If the p is low, the null must go. If the p is high, the null may fly, or the null will fly. What we're really looking at, if I'm doing a calculation, let's say I'm doing a right-tailed test. If I was doing a right-tailed test and I find my test statistic, and so our test statistic was z equaling something. I'm not even going to worry about finding a number. If I calculate out what the probability of that is, and if I say that I'm doing a right-tailed test and I find my probability out here to be something like 0.001, well, is it very likely that if I'm saying the mean equals some number is my hypothesis, if I'm saying the mean is equal to this and the probability that my sample I find gives me a 0.001 chance of that happening just randomly, that is so slim that my assumption that I know my original mean had to be wrong. On the other hand, if I'm calculating this out and I find my p-value to be 0.2, well, if I found that I think the mean is this number and the probability that I get a sample that gives me that test statistic or more extreme is 0.2 or 20% chance, well, 20% chance, that's pretty high that can just randomly happen. So I don't know anything about my original claim. I can't reject it because it's not way off from it. But it doesn't necessarily tell me my mean was right. It just says that it's not so far wrong that I have to reject my original hypothesis. And so that's what this is telling me. If my p-value is low, then that null must go. I have to reject my original statement. The other hand, if my p is high, the null will fly. I will fail to reject that null hypothesis. So when we're trying to find the p-value, as I said, the p-value matters if I'm doing a left-tailed, a right-tailed, or a two-tailed test. If I am trying to figure out that I'm doing a left-tailed test, the p-value is the area to the left of my test statistic. So we looked last time of how to find the different test statistics, and we will spend more time working with each one of those as we go through their various sections. But we'll find their test statistic. And then if it's a left-tailed test, remember left-tailed comes from my alternative hypothesis saying things like the mean is less than whatever that number was. Our null hypothesis would have been that the mean equals that number. And this is assuming I'm doing mean. You could do the same thing with proportion or standard deviation. If I'm doing the less than, then I'm doing a left-tailed test for my alternative hypothesis. Then I'm finding my probability to the left of that test statistic. If I'm doing a right-tailed test, then my p-value is the area to the right of my test statistic. And so that's when I have an alternative hypothesis that it's greater than whatever that value is. So each of those are just looking at their two extremes. If I'm doing a two-tailed test, The two-tailed test means I can reject it if it's in either one of the two tails. If it's too little, I'm going to reject it being equal. And these come from when I'm saying my mean is equal to some number is my null. My alternative would be that the mean does not equal whatever that number is. Again, mean, standard deviation, variance, it doesn't matter, proportion. But if I'm making a statement about those being where my alternative is that it's not equal to, then if it's either one of the two extremes, too small or too big, I'm going to reject this statement. And so we have to do possibility of two different sides. So the next thing is my test statistic on the right side or the left side? If my test statistic is on the left, then I find the area to the left and I double it. And that's the key piece to pay attention to on this one, because if it's the area to the left, I would reject it if it's this side, but we're going to have the same space on the other side. So we have to double that area because it's a two-tailed test. If it's on the right side, we will double whatever we get as the area to the right of that test statistic. One of the common errors is that you guys forget to double it. Or you get so extreme, you just get in the habit of doubling it all the time that when you get to a left or right-tailed test, you double it when you shouldn't double it. So pay attention to what you want to use. This figure is figure 8.5 that's in your book. So you can still refer back to this. Actually, is this on your reference sheet? It is. It's also on your reference sheet. So this flow chart's on your reference sheet. So if you're working on your test and you don't remember, do I double it or not, you can look through and figure out what you're supposed to do on those. So let's look at an example on number 30 on page 410. So I want to find the p-value. Use the given information to find the p-value. Also use a 0.05 significance level and state the conclusion about the null hypothesis, whether we're going to reject or fail to reject the null hypothesis. So on number 30, the test statistic in a right-tailed test is z equaling 2.50. So I'm looking at a right-tailed test, which means from what we talked about before, if I'm doing a right-tailed test, what do I find for my p-value? I find the area what? Right-tailed. Find the area to the right of the test statistic. And so on this one, I want to find the area to the right of this test statistic. My test statistic is 2.50. So from knowledge you have before, what do? If it's a z-score, what table should we use? Okay, should be using A2. We're going to use that normal distribution. If I know my test statistic is z equaling 2.50, finding the area to the right, take the number and subtract it from 1. So what is the probability to the right of z being 2.50? So the area to the left on your table, this area over here was the 0.9938. So this is going to be the 1 minus the 0.9938, which you said was 0.0062. Okay. Questions on doing that? So this is telling me, because it's only a right-tailed test, I do not double anything. So my p-value is the 0.0062. So the probability that I would have whatever the original statement was, and in this case it's either talking about a proportion or a mean, if I was giving the original null hypothesis saying that p equaled, the proportion equaled some value, and then I have a sample that I calculate out, and the test statistic is this 2.50, the probability that my original statement of the mean or the proportion equaled that number is true, and I get this sample, the probability is only 0.0062. Is that very likely to have occurred by random chance? That's a really small p-value. And they told us to use alpha as 0.05. That's significantly smaller than 0.05 because this is less than a 1% chance that that would happen just by random chances. This tells me I have to reject my null hypothesis. I'm rejecting the fact that my original assumption that I knew the population proportion or mean was wrong. If the p is high, the null will fly. If the p is low, the null must go. And so this is a very small p-value, so the null hypothesis must go. It will be rejected. Questions on that one? Okay, let's look at number 32 then. On number 32, the test statistic in a two-tailed test is z equaling negative 0.55. So, first of all, where do I even start? Say that again. You're not going to divide that one by 2. No. Okay. Let me go back to our little flow chart. Okay? Got a two-tailed test. Is the test statistic on the left to right? It's on the left side. P-value is twice the area to the left of the test statistic. So I've got to find the area to the left of that, and I've got to double it because I'm taking whatever's on this side and whatever's on this side. Because it's a two-tailed test, if it's either extreme, it gets to be thrown out. Because I'm assuming that I know what it equaled in the original plane. And so we're going to have to figure out what is, figure out, first of all, what is the area to the left. And my p-value is going to double whatever that is. So what is the area to the left of negative 0.55? 0.2192. Say it again. Okay. Is everybody agreeing with that? I grabbed the wrong paper. Okay, so then what does that tell me about my p-value? I have to double that because if it was in this extreme over here, we also have that 0.2912. We have to double whatever we're getting because we have to throw it out for either one of those two extremes. So what is that, 0.5824? So is that a reject or is that a fail to reject? Is that likely to occur just by random chance? It's very easy. I got a 58% chance that I could have just had a sample where I knew what the mean was, the population mean I picked was right, and I just randomly get the sample, 58% chance that that sample would have come out to being what it was. That's a really high probability that it could just randomly have occurred. Definitely significantly more than 0.05. And so this is a fail to reject. That fail to reject is saying I cannot throw out my original assumption as being wrong, is what we're really looking at doing. Questions? We will be walking through how to get our test statistics and then find the p-values and being able to make our decisions on individual problems for each one of the different styles, for the proportion, the mean, with and without the standard deviation, and the standard deviation variance. So we'll be walking through the whole process on several of these different problems. This chapter, this section is kind of giving you a general overview of what's going on each piece and what you need to use. Don't confuse your p-value with your proportion p. Your p-value is finding a probability of getting a test statistic at least as extreme as the one representing the sample data, versus the p is your population proportion. P hat, remember, is also your sample proportion. These are telling you complete different things. Population proportions tell me the proportion from the original population, what proportion of them meet that criteria. That's always going to be a decimal, but it's representing that percent of the people or the percent of that group that meets that thing. Versus your p-value is telling you a probability. Also will always be a decimal, but it's representing something different. And so pay attention to what you know and what you have. So even though you just see p on there, you don't just immediately think it's p-value or proportion. You have to know which one of them you're dealing with. Based off the problem that you're in, if you're paying attention to what you have, you should be able to tell the difference of which one of those it is. All right, conclusions. We always test the null hypothesis. The initial conclusion will always be one of the following. Either you will reject the null hypothesis or you will fail to reject the null hypothesis. Those are our two conclusions that we can draw. Now, what we can do with it afterwards and how we word it into common day language, we're going to look at that in just a little bit. But the original, what we're testing, is always testing that null hypothesis. And our null hypothesis is always that some value equals some number. And we're testing whether that is going to be able to be rejected or fail to reject that value. We have two different ways to make this decision. We can use the p-value method or we can use the traditional method. The p-value method is to find the probability and then compare that probability to the to your alpha. So if it's 0.05 or if it's 0.01 or if it's whatever percent you're looking at as being your alpha value. So finding your probability that it would occur. So that's what we just looked at, was finding that p-value, and we even looked at whether we could reject or fail to reject our decisions as our decisions. The traditional method is another method that we could use. I guess right now let's go and look at the p-value method a little bit more. P-value method, using the significance level of alpha. If our p-value is less than or equal to alpha, we reject the null hypothesis. If my p-value is greater than alpha, then you fail to reject your null hypothesis. If your p is low, the null must go. Reject the null hypothesis. If the p is high, the null will fly. You'll fail to reject your null hypothesis. So that's using your p-value method. Now, if you're using the calculator, and eventually we'll be looking at the calculator with each of these different, well, out of 3 of the 4 different methods, there's not a calculator shortcut for the standard deviation again. But if we're using the calculator will use the p-value method. It'll calculate out the probabilities for you, and you have to compare that p-value to your alpha to decide if it's a reject or fail to reject your null hypothesis. Be able to do these calculations by hand also, because I will be looking for both of those kind of things in different problems. The traditional method is a different way of doing it. If you're doing it by hand, the traditional method is the easier method to do. If the test statistics falls within the critical region, we'll reject our null hypothesis. If the test statistic does not fall within the critical region, we will fail to reject the null hypothesis. So last time we looked at finding the critical regions. If I know I wanted to have, let's go with a two-tailed test. And I want to be 95% confident, so let me just use alpha as being the 0.05. So that'll be the way it's listed on these. If I'm doing a two-tailed test and alpha is 0.05, we looked at doing this one last time. If it's a two-tailed test, what that's saying is I want in my two tails to have the probability that it's rejected is the 0.05. Well, if it's 0.05 between the two tails, that means this one is the 0.025 and this one is the 0.025. Well, what is the z-scores, so I'm going to go ahead and just use the z-score on this one. What's the z-scores that give me those two critical regions? So what is the z-score? Let's find this one over here first. That gives me 0.025 to the right, so 0.975 to the left. Okay, 1.96. And what would be the z-score on the other side? Because it has that nice symmetry, so it's the negative 1.96. So my two critical regions are these two things here. If I have a z-score, if I get a test statistic that is going to be in either one of these critical regions, so it's so far away from the middle section, from the mean or the value that we had in the middle, if we get into one of these two tails, we're so extreme out there, then that's in our reject the null hypothesis. If I get something that's not in my critical region, if I get something here in the middle, that's a fail to reject my null hypothesis. So if I'm doing it by hand, I was waiting for you guys to catch up with me on the 1.96 and the negative 1.96 because we've done those so many times that they're kind of getting ingrained into your head. That to find these two critical values and know where my critical region is, if you're using alpha several times, then just you immediately know where the critical values are, and the only thing you need to find is what is my test statistic? What is my z-score? And if my z-score falls in these extremes, we're throwing out the null hypothesis. If it doesn't fall in those two extremes, then we're failing to reject that null hypothesis. So we looked at the critical regions last time. So let's do a couple of problems where we do each one of these different methods. So if we look at number 30 on page 410, so we already did number 30 on page 410 with the p-value method. We found the probability that we were so extreme. If I'm doing the p-value or doing the traditional method on number 30, we know alpha is 0.05. On number 30, is it a left-tailed, a right-tailed, or a two-tailed test? Okay, on number 30, it's a right-tailed test. Which is telling me that all 0.05 of my probability is just in that right tail. So I'm not throwing it out if it's too low. I'm only throwing it out if it's too high. And so I need to find where is the critical value that cuts off having 0.05 on the right side. So all 0.05 is over here. So what am I looking up in my tables? If it's 0.05 on the right, then it's how much on the left? 0.95. So what is the z-score that gives me 0.95 on the left? My graph's off just a little bit. Questions there? Now that I have that, now I get to look to see what is the test statistic. The test statistic on number 30 is z equals 2.50. So if 1.645 is here, 2.5 is over here, so my critical value is the one, that's a C there. The critical value is the 1.645. My test statistics, 2.50, is that in the rejection or the fail to reject region? That's my rejection. That's way extreme out there. If it's way extreme, we're rejecting this. It's way far away from where the middle value was. And so this is what I'm assuming to be true. If I know that the mean or the proportion is this value, this is way out there, more extreme. And so that is my reject the null hypothesis. Same conclusion we came to a little bit ago. when we found that p-value to be, what was it, 0.001? Wasn't that the number we had a little bit ago? 0.0062. So earlier, we rejected the null hypothesis because the p-value was extremely small. Now we're rejecting the null hypothesis because it's falling in my critical region. So two different ways to do the same problem, you come to the same conclusions. You will have to do the traditional method when we get into doing the standard deviation and the variance method of doing things. Your calculator can do some of the p-value, but I'm going to be asking you guys to do some of these things by hand as we do them. So understanding where things are coming from. And in this first section, I'm not going to teach you anything with the calculator, so you're going to have to do these things by hand. If we do number 32 by hand, doing the traditional method. On number 32, we still have the alpha is 0.05. We have a two-tailed test, and my test statistic is that z was what number? Negative 0.95? Okay. So now if I'm doing the traditional method, if this is a two-tailed test, then if it's either one of the two extremes, it can get thrown out. And so if it is in this left extreme, or if it's in this right extreme, I can throw it out. So I want to take my alpha and cut it into 2, because if it's either one of those extremes, we're throwing it out. So 0.05 cut in 2 is 0.025. What is my z-score that gives me 0.025 in my two tails? So my critical value is the 1.96 and the negative 1.96. Questions there? Now I have to figure out where did my test statistic land. My test statistic is the negative 0.55, so it lands right about here. So is that in my rejection or my fail to reject region? This is my fail to reject. That could easily happen just by random chance, that we can get something that's that far off away from the true mean, even if I knew what the true mean was. And so in this case, this is a fail to reject. And we fail to reject the null hypothesis. And when we're doing the entire problems, we will know what the null hypothesis was. And we will be able to come to a better conclusion on what that means in non-statistical sounding terms, which will be part of what we'll do later. Questions there? Now, if we talk about the wording, we have to be very careful with how we state our conclusions. On your reference sheet is this exact diagram. So we've got calculating out your p-value. Right below that is how to word our final conclusion. Make sure when you make conclusions, you follow these words. So, first question. From the original claim, and it is the claim we are looking at, not our null hypothesis, not our alternative hypothesis, but what was the original statement claiming? Did the original claim contain equality, or did the original claim not contain equality? If it did not contain the equals, then that's the same thing as your alternative hypothesis. If it did not include the equals in there, then the next question is, did I reject or did I fail to reject the null hypothesis? If I rejected it, then I can say that the sample data supports the claim that blah, 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 blah. So whatever it was that we were claiming to be true, which did not include the equals. So the sample data supports the claim that the mean age is greater than 25. So we can make that statement. That is the only time I truly get to support an original claim, where I can really say that claim was right. Because I've rejected my null hypothesis that it was equal, which is what I was assuming to be true. I've just got something so far extreme that it couldn't really equal that value. So it had to be greater than that. The next option, if I rejected the null, it did not include equals. I rejected the null hypothesis. It was not true, so I failed to reject the null hypothesis. I can say there is not sufficient sample evidence to support the claim that the mean age is greater than 25. If I had the original claim included the equals and I rejected it, then I can say there's sufficient evidence to warrant rejection of the claim that the mean age is 25. So here I'm actually rejecting that claim. And this is the only time when I completely get to reject the original claim. Compared to if I fail to reject it, I can just say there's not sufficient sample evidence to warrant rejection of the claim that the mean age is 25. But you will put in whatever the original claims are. You're having to put that in there of what you were trying to state, and it's the claim, not your null hypothesis, not your alternative hypothesis. So never conclude a hypothesis test with a statement of reject the null or fail to reject the null hypothesis. Always make sense of the conclusion with a statement that uses simple, non-technical wording that addresses the original claim. But we have to be careful with what we're saying because we can't make it sound like we're making a conclusion that wasn't there. So that's the reason why we have these type of things, or putting it in non-technical terms, but you have to be careful with what we can say. So those will be the final conclusion that you can draw, that you have to go back to using what the original claim said. So if we look at a couple examples, if we look at number 38. We look at number 38. The original claim says the percentage of on-time U.S. airline flights is less than 75%. The initial conclusion is that we're rejecting the null hypothesis. First of all, from my original claim, what is my null and my alternative hypothesis? So first of all, what is my claim even saying? Okay, which part is less than 75%? P, mu, or sigma? Is it a proportion, a mean, or a standard deviation? Okay, it's a proportion. Anytime you're given a percent, you're given a proportion. So I'm saying my proportion is less than 75%. So then what is my null hypothesis? Null is always equal. What is my alternative? No, it's not equal. It's less than. P is less than the 0.75. Because remember, to find your alternative, you're saying whichever one between the claim and if the claim was false, which one does not include the equals. So since this did not include the equals, we're just going to use it as my alternative. Now, the next piece we have is that we are rejecting the null hypothesis. So, did my original claim have equals in it? Okay, this did not include an equal. So if we go back to my reference, it did not include the equal. We just rejected the null hypothesis, which means we're using this piece right here. The sample data supports the claim that the percentage of on-time U.S. airline flights is less than 75%. And that's how we would word that one. Just coming and using this as the first half of the sample data supports the claim that, and whatever your claim was, which in this case was that the percentage of on-time U.S. airline flights is less than 75%. If we look at number 40 on page 411, the original claim is the percentage of Americans who believe in heaven is equal to 90%. Our initial conclusion is to reject the null hypothesis. So first of all, what is my claim? What about 90%? Percentage of Americans who believe in heaven is equal to 90%. So it's going to be equal to your 90%. What's equal? P again. This is a proportion again. And knowing that's important, you can't just say equals. You've got to tell me what equals. If that's not true, if this is false, then we're going to say that it's not equal to 0.90. So what is my null hypothesis? Null is always equal to. What is my alternative? Alternative is that it's not equal to. So now, from the original claim, the claim had that it was equal to. And these two pieces are not necessarily asking for in this problem, but it would be something you'll be doing later. The original claim had the equals. So my original claim included the equals. On this problem, I rejected that null hypothesis. So there is sufficient evidence to warrant rejection of the claim that the percentage of Americans who believe in heaven is equal to 90%. Now, from that statement, I don't know if it's more than 90% or if it's less than 90%. I just know it's not equal to 90%. But this is actually rejecting that claim that it was going to be equal. And those are the two most solid conclusions that we can come to. The other ones that we're looking at are leaving you more questions than they do answers as we do these. I'm not going to ask you for the type of errors, so we'll talk about the type 1 and type 2 errors next time. So there's your guys' homework. Registration for classes begins tomorrow, so if you have not met with your advisors, you should be doing that soon, so you can sign up for your summer and your fall classes. Please do complete your course evaluations for all your classes, but especially this one. And our test is going to be on April 15th. Don't come to class Friday because I won't be here to teach anything. The ARC is still open tomorrow, though.